I'll let the team know. Thanks. Yeah, they're doing it now.
Yeah,
Is this
thanks a
better?
lot.
Is this better?
Yeah, thanks.
Great, great. Okay, so this action has this U1 symmetry. U1 because this is a unitary matrix, 1 because this is just one number. U2 will be 2 by 2 unitary matrix, U3 is 3 by 3 unitary matrix, and so on. So this is a U1 symmetry, and this is obviously invariant under that, right? Because this now is not a function of x, it's just a global U1 symmetry. So there will be an e to the I alpha here, but psi bar, remember, is psi dagger gamma 0. And when you take a dagger, e to the minus I alpha comes out. And so this is a symmetry. So this is a global U1 symmetry. Okay. So here alpha is not a function of x. So this is a global U1 symmetry. Okay. But now, again, in the flavor of what we've been doing, and also independently, you say, I want to be more greedy. I don't want this U1 symmetry to be global. I want a local U1 symmetry. What if psi goes to e to the I alpha of x psi? Okay, I make this symmetry local. So then is this action invariant? Let's check. S Dirac will transform to integral d4x psi bar e to the minus I alpha of x times I gamma mu del mu minus m e to the I alpha of x psi. Right? Now the e to the I alpha won't just go through and hit and give 1 because there is a del mu sitting in between. Right? So what will this give? So this will be integral d4x psi bar e to the minus I alpha e to the plus I alpha times I gamma mu del mu of psi minus m psi. But there's also an additional term which has a plus I gamma mu and then I del mu alpha times psi. Okay. So simplify that. So this is integral d4x psi bar I gamma mu del mu minus m when you take a symmetry, it's globally a symmetry, and then you make it a function of x, which is to say at every point in spacetime you put a U1, right? That's what you call a gauge U1 or a U1 gauge group. So anyway, local U1 is not a symmetry. Of S Dirac, written this way. Okay. But now you say, I'm still greedy. I want this to be a symmetry. Okay. I want local U1 to be a symmetry. Tell me what I should do such that local U1 has to be a symmetry. Okay. What should I do? Exactly. So what should I do such that it is a symmetry? Okay. And as Athar was saying, what you should do is to cancel this extra term. Okay. To do that, what I should do, I mean, notice that why did this extra term come? It's because this del mu acted on e to the I alpha and gave an additional term. Okay. So del mu acting on e to the I alpha of x psi did not go to e to the I alpha of x del mu of psi. That's the root of this problem, right? Because if this had happened, e to the I alpha will come here, cancel this e to the minus I alpha, it will be a symmetry. So can we construct d mu of psi? Oh boy, I'm using d mu for something else, right? Okay, this is a brief digression. There is no GR here. So this d mu will not be the covariant d mu, but this will also be called a covariant derivative. Okay. So can we construct a d mu of psi such that d mu of psi transforms to e to the I alpha of x? Can you do this? And you notice that that's actually easy to do, right? But to do that, you have to introduce something new, right? Let us say d mu is actually del mu plus some a mu. Okay. Then d mu of psi transforms to what? So d mu of psi, which is equal to del mu plus a mu on psi, transforms to del mu plus a mu on e to the I alpha psi, which is equal to e to the I alpha of x. So this transforms such that a mu also transforms. I have not told a mu is some new field I've introduced, and that also transforms under e to the I alpha in some way. Under this u1, it also transforms in some way, and we don't know what that way is. We want to fix it such that this happens. Okay. So this will be e to the I alpha, and then you'll get a del mu psi, and then you'll get this annoying extra term, which I want to cancel with an a. Now, if a prime mu is equal to a mu, let me say minus here, minus I.
In the first line of this, so you want d mu psi to go to e to the I alpha d mu psi.
D mu psi, yeah, indeed. Sorry, thanks. Thank you. So I mean, this is just some number. Let me choose minus I alpha. That's the convention. So get a minus I alpha here. Okay. Now you notice that if this is true, this a prime mu is a mu plus del mu alpha. When you get the plus del mu alpha, that will cancel this term. Okay. Then d mu alpha, sorry, d mu psi will be exactly e to the I alpha of x d mu of psi. Okay. And thus, S Dirac defined correctly, let's call it prime, defined as e to the d4x psi bar I gamma mu d mu minus m psi is local U1 invariant. Right? You see what I've run, right? So my greed has cost me something. The greed that I want a local U1 symmetry has cost me the introduction of a new field. I had to bring in a new field a mu, which under this U1 transformation transforms like this. Okay. Then only and only then can I write down a gauge invariant action. But now we have discovered a new field. You have to write down an action for that field as well. Okay. And that should be invariant again. That every action that I write down should be invariant under that U1. Okay. And I have discovered that a mu transforms under a U1 like this. So I have to write down an action that's invariant under this also for the A. No, it's a Lorentz vector. It's a Lorentz covariant vector. So form, one form. Okay. So gauging U1 or making the U1 symmetry local, that's just a fancy and quicker way of saying making the U1 symmetry local. So gauging U1 has forced me or forced us to introduce a field a mu that transforms under the U1 as a mu going to some a mu prime, which is equal to a mu plus del mu lambda, del mu alpha. Okay. Now for this field, I have to write down an action. Okay. And that action should be invariant under this transformation. what is a combination that's invariant under transformation? This transformation. F mu nu defined as del mu a nu minus del nu a mu is invariant under this. So the simplest action I can write down for this field will be F mu nu, F mu nu. So gauging a U1 has forced the electromagnetism upon us. Okay. Gauging U1 has forced electromagnetism upon us. Or another way of saying is that U1 gauge theory is equal to electromagnetism. Okay. So this is the simplest example of a group being gauged to give you something new. Okay. So in our example, remember, we have to gauge Lorentz transformations. Okay. And we'll see that if I do the same procedure, the theory I get out of it, so gauging Lorentz transformation gauge theory, and I have to also do coordinate transformation for gauge theory. So Lorentz transformation, LLT plus DCT gauge theory will be gravity. So gravity will be, just like electromagnetism here was forced upon you by U1 gauge theory, gravity will be forced upon you by LLT GCT gauge theory. Okay. So that's the end of this digression. End of digression. Now let's come to a recap of last time, and let's come to our problem of coupling fermions to gravity. Okay. So what have we learned so far? In the first class, we have learned that there is a Dirac action. And psi bar is just psi dagger gamma 0. Gammas are defined such that they satisfy something called the Clifford algebra. This is called the Clifford algebra. And psi transforms under a Lorentz transformation as exponential I over 2 mu S mu nu psi, where omega mu nu is just lambda mu nu, you write as some identity plus omega mu. Okay. And these S mu nu were just the generators of this Lorentz transformation. Just like that. Okay. This is the quick recap of first class. This what we mean by a spinor is anything that transforms like this, where all these stuff are defined that way. And the simplest action you can write down for such a spinor, or the simplest scalars you can find from such a spinor, is that. Okay. That's what we learned in the first class. Yesterday, what did we learn? Yesterday we learned that in order to describe local rest frames and to define these local Lorentz transformations of gravity, we discovered that there are local Lorentz transformations of gravity. And to do that, we had to introduce VL binds, co-VL binds, and spin connections, right? We found that there are these VL binds, there are these EA mu's, which under a local Lorentz transformation transform like this. And then we also found that there should be some omega AB mu, which in terms of these is defined as EA nu, grad mu, EB nu. I hope I'm defining this correctly. Could you just check from your notes? I mean, there could be an additional minus sign outside. That's just convention. I don't want to mess up the convention. Is it fine, right? I think this is fine. And we found that omega under the same local Lorentz transformation transforms like a gauge field. It transforms like this. Okay. So see, if you had done this digression wala exercise for local Lorentz transformations, what you'll have ended up discovering is general relativity. But we already know general relativity, and that's how we found this, right? So you already see that there a mu had to transform like a mu plus del mu of alpha, where alpha is the gauge transformation parameter. Here the gauge transformation parameter is lambda. So we already know the field which transforms like that. So now our job is easy. Our job is to just make this covariant derivative. Where is the covariant derivative? This covariant derivative, right? And that I can do with just this omega, as I'll show you. Okay. So now let's try to write down a Dirac action, which also includes for gravity, which couples the fermions to gravity. Let's take guesses. So S Dirac coupled to gravity should be, of course, the invariant volume element should have a root minus g. That much is always clear. And then you have I gamma mu del mu. But then all this work last class, was to show that these gamma matrices should be defined on a locally flat space. So gamma matrices should really have an A index, right? But then I have to also contract it with a del mu. And what lets you go between frames and coordinate components? It's this, right? Because this has one frame index, one coordinate index. So that you have to put here. So till now things make sense. And then you just put a minus m. Psi bar. Okay. But this has the problem that we faced while gauging, while making U1 local, right? The del mu, so now psi transforms how? Psi transforms as exponential I over 2 omega s. What indices should I use here? What indices do you think I should use here? Should I use A underline B underline unit indices, or should I use mu unit indices? Exactly. So these S's, remember, I wrote it down here, are just linear combinations of gamma matrices. And again, gamma matrices has to be defined locally on a local rest frame. So you have to use the local rest frame to define all of this. Okay. And the Lorentz transformations are also in the local list. But now this is a function of x. That's the complication, right? When I made alpha of x, here I'm making many copies of alpha. There are like 6 of them, and they're all functions of x. Now, if I put this in here, same problem will arise. The del mu will act on the omega and will give you an additional omega, right? So here too, we need a covariant derivative. Yeah. Local Lorentz symmetry. Good question. You're saying what is the Noether charge of the local Lorentz symmetry? So I guess there should be 6 of these charges. Okay, I haven't thought about this. I'll get back to you. I should think about it. Probably something easy. I mean, you can sit down and compute it. So, okay. I'll come back.
For global Lorentz symmetry, they are just angular momentum.
No, he's asking in right. Yeah. Yeah. That's the answer. So look, as Sridhar is saying, global Lorentz transformations, I'll just give you angular momentum, right? The full angular momentum. So I mean, locally you don't ask for a symmetry, right? Like, so when you're saying e to the I alpha of x is a symmetry, you introduce a gauge field. That's a gauge symmetry. Gauge symmetries are not really symmetries. So they won't give you Noether theorem. Well, there are 2 Noether theorems. They'll give you another Noether theorem, but let's not worry about that. Yeah, thanks. Yeah, okay. So we need another covariant derivative. So what we can do now is the same exercise and discover covariant derivative. But what can it contain? The d mu can contain a del mu. In all the examples so far, general relativity or electromagnetism or here, it's just del mu plus something. Okay. So what can it be? The plus something should depend on omega. So let me write omega. But omega has also these frame indices which get contracted. And the only way I can do that is to contract with the EB. I can't contract it with another omega because if I put another omega, there'll be another mu index and I would have to contract that. But I have to have a free mu index. So the only way to do that is this. And then there will be some factor here, which you have to fix such that this will be invariant. Okay. So if you were doing this computation, you just put an alpha here, put it back there, do the computation, fix alpha such that it's invariant. I've already done this computation, so I can give you the answer. It's just I by 2. Okay. So S Dirac coupled to gravity should really be, so this is a question mark, that's wrong. The answer should really be d4x root minus g psi bar I gamma mu E a mu times this del mu plus I over 2 omega a b mu SAB minus m psi. That's the answer we've been looking for 3 classes. Gamma A, indeed. Thanks. Right? So this is LLT and GCT invariant. GCT invariance is very easy to see. These size don't have indices, so size transform scalars. And this transforms as a upper index vector, this transforms as a lower index vector, so GCT invariant is obvious. LLT invariance, you have to do some work. You have to take this, put this in here, expand to first order, put this in here, and then there'll be so many terms because this will also transform in this way. So you have to keep everything to first order in omega and do this computation. This took me like 3-4 pages. I can do this on the board, but I had requests not to do it on the board. But if you want, I can do this on the board. Take some time, probably take 40 minutes if I don't make mistakes. Okay. Anyway, so we are basically done. This is what we wanted to achieve. But yeah, you can go back home and check that what you have to do here is to repeat that calculation. Where is that calculation? This calculation, right? You have to transform this S Dirac such that psi bar will transform as the opposite of this, and then EMU also will transform because that will get a lambda AB, and then this del mu will not transform. This del you're not doing GCT, you're doing local Lorentz transformations. Omega will transform. SAB just constant matrix will stay as it is. Psi will transform this way. Put everything together, keep everything in order capital omega, cancel. Okay. In doing that, you would have to discover many things, which is why I wanted to do this computation, but it's okay. You have to discover the commutation relations of gamma and S and S and S. But all of that you can sit down and do because I had given you last time what gammas look like. I'd given you 0 identity, identity 0, sigma I 0 sigma e minus sigma e 0. And then you can take their commutator to find the S, which also I wrote down. And then from the S, you can find their commutators. And in doing that, you'll discover the Lorentz algebra. Okay. And then you can do this computation. But anyway, I leave it here. You can figure this out. And if you have questions, you can come ask me. So we have really achieved our goal, which is what we wanted to do, is the question of asking, how do you couple spinors to gravity, right? It's not so straightforward as in scalars or vectors, because scalars or vectors had their indices, or they transformed as tensors, and tensors are easy to couple to gravity. All you need to do is make the del mu's d mu's and make d4x root minus g. Then you write down an action. In the case of spinors, we discovered that spinors are defined with respect to a Lorentz transformation, and that Lorentz transformation has to be defined locally in gravity. And then we have to learn how to do that, which is Vielbeins, co-Vielbeins, and spin components, spin coefficient, spin connections. We did all that, and then we have finally written down an answer where things are correct, things work nice. So now this is what you will use to understand, for example, an electron field in an expanding universe. Okay. Because an electron is a Dirac spinor, and you have to put it in an expanding universe, and an expanding universe is a generally curved spacetime. So yeah. Let me also note that this other point that I was making, that you would have discovered electromagnetism if you did a U1 gauge theory. If you had done this calculation, and if you didn't know that, gravity existed, you would have to postulate such an omega, and then you have to find how omega transforms such that this remains invariant, and you would have found this. Okay. And EA, you would anyway need to contract this index. So you would have found both Vielbeins and spin connections. And then you say, I'll write down an action for EA and omega such that that is invariant under these Lorentz transformations. And you will discover Einstein-Hilbert. Okay. You'll discover root minus dr. And hence you will discover the Einstein equation. But anyway, I'll stop there. This was a quick class. I would have liked to do this computation, but I'll leave it to you. Okay, any questions from online? Okay, thanks.
Thank you.